Good morning, children. Welcome to online chemistry class of class 12. Today we will start our new chapter, that is your chapter 9, coordination compounds. Okay, please do write that what I am telling, the chapter name coordination compound, and sub units what we have to study over here, the IUPAC nomenclature followed by the structure, different terms related to coordination compounds, for example coordination sphere, coordination entity, ligand, and all these other related terms. Difference between a double salt and a complex salt, Warner's coordination number theory. Next is the bonding approach, valence bond theory approach and crystal field theory approach to describe the bonding structure and various properties of coordination compounds. Finally, the stability of coordination compound, including the explanation of bonding in metal carbonyls, and then the uses and applications of coordination compounds in various fields. Now let's start with the first topic, that is what is the difference between a double salt and an addition compound and a complex salt, sorry. Now this is called addition compound. Here in addition compound you will see that I marked the salts. It's actually what, when we take two or more compounds, might not be always salt, might be one is salt, another could be the gas. So anyway, when we take two or more substances in stoichiometric ratio means simple whole number ratio, and then after taking this, when we take the common medium water followed by, then the solution is formed and then we carry out crystallization. Whatever compound is formed, this is called addition compound. So how that addition compound is being formed? By mixing two or more components together, adding the common medium water to them, followed by crystallization. Then whatever product is there, we call it as addition compound. This addition compound is actually two types. One is the double salt and the second one is the coordination compound, or that is more commonly known to us as complex salt. Let's see the basic difference between the double salt and the complex salt. The first point of difference is, in a double salt, we always have the components, might not be salts, the components in 1:1 ratio. Without this 1:1 ratio, it is never possible to have a double salt. While in complex salt, they might be in 1:1 ratio, or they might be in 1:, any other ratio, say suppose X. And this X is of course not equal to 1. For example, let's take this one. When we make more salt, we know more salt is ferrous ammonium sulfate. The two salts that are the components are ferrous sulfate and ammonium sulfate, and crystallization is done, then we have 6 units of water of crystallization. In this, the composition or ferrous sulfate and ammonium sulfate are always 1:1 ratio. So it is a double salt. In case of potassium ferrocyanide, a complex salt, the constituent materials are potassium cyanide and iron 2 cyanide or ferrous cyanide. In this, it is found in the ratio of 4 moles of potassium cyanide for every mole of iron 2 cyanide. Then only we are having 4 potassium, 4 plus 2, 6 cyanide and 1 iron. So then we could see that it is not having 1:1 ratio or equimolar ratio between the components, that is the complex salt. The next one is, when the double salt is dissolved in water, each and individual ions are showing their existence in aqueous solution. For example, when we take the aqueous solution of more salt, as this is your experiment also, practical also, so I am taking this example, it will be easier for you. When we take the aqueous solution of more salt, we get ferrous ion, ammonium ion and sulfate ion, all these 3 as the present in the aqueous solution. But at the same time, when potassium ferrocyanide is ionized or taken the aqueous solution, it dissociates to the whole complex ion called the ferrocyanide ion, and its counter ion is K+. So since ferrocyanide ion has a valency of 4+, then it's obvious that it will have a valency, means K+ is 1, then there will be 4 potassium ion and 1 ferrocyanide ion. This is called the complex ion, while this is called the counter ion. Thereby, what we could have, that potassium ferrocyanide altogether dissociates to 5 ions, 1 complex and 4 counter ions. The next very important thing is what we were doing, that is why that complex salts are also known as coordination compounds. This is because there is always a coordinate bond that is present in the formation of such complex salts. This coordinate bond might be present, might not be present in this. Now when we consider this potassium ferrocyanide, in this Cn- ion is called the ligand, while Fe2 plus, what we are making, this is called the central metal. There is a point. All ligands are necessarily be the nucleophile. That means all ligands are either negatively charged or having the lone pairs of electron, while the central metal is necessarily a D or F block element. Means they are having incompletely filled D orbital, or they are having the incompletely filled, partly filled F orbital. As you know, in a coordinate bond, the ligand will provide the shared pair, while means it should be electron rich. Or it should be, what I said, it should be nucleophile. Then only it will be able to provide the shared pair to it, and the central metal which is taking the electron pair for sharing. It is not a ionic bond in which a complete transference would take place. This must have the vacant space, and since the d or f orbitals are partly filled, these are having the empty orbitals or vacant space to accommodate the electrons. It means that this particular species, what we were doing is, this is the central metal, as it is having the partly filled d or f orbital. It has enough space to accommodate the electron pairs as shared pairs provided by the ligand. Therefore, this vacant space to adjust or to accommodate the electrons make it acceptor species, while the ligands are the donor species. I repeat, it is not forming, this arrow doesn't stand for any complete transfer of electron from ligand to metal. It is only the representation of coordination bond in which the shared pair is only given by the ligands, while the central metal is taking only the central metal is providing the vacant space and ligand is providing the extra electrons for sharing. Ultimately, once the coordinate bond is being formed, it is exactly behaving as simple as the covalent bond. So, just in covalent bond we had the mutual sharing. In coordinate bond we will have the sharing little unequal, means both are sharing, but one is sharing the electron pair, another is sharing the vacant space. That's all. So, in coordination compound, we might not have, in coordination compound we will always have the ligand to metal coordinate bond, but in double salt we might not have any such coordinate bond. We may have, like if ammonium ion is there, as we know ammonium ion is always associated to a coordinate bond NH3, and that lone pair of electron is forming NH4 plus. So it is possible that it is having any coordinate bond. So what is written over there, that it may or may not have coordinate bond, but coordination compound is formed through ligand to metal coordinate bond. So that is, in this ferrocyanide, the 6 cyanide forms 6 coordinate bonds with 1 Fe2 plus. And in ammonium ion and other examples are also there, of course, which could form the coordinate bond. Okay. So this is how we are describing this difference between a double salt and a coordination compound or a coordinate bond. Now coming to one question. Question number 9.2, exercise question. The page numbers may vary. Ferrous sulfate solution mixed with ammonium sulfate solution in 1:1 molar ratio. So wherever you will get 1:1 molar ratio, we are having two options. It could be double salt, it could be complex salt also. Okay. Gives the test for Fe2 plus ion. Now this is the ultimate finding of, or ultimate identification of a double salt. It is in 1:1 molar ratio, could be double salt, could be complex salt. But since it is giving the existence of Fe2 plus ion, it is obvious that it is a double salt. But copper sulfate solution mixed with aqueous ammonia in 1:4 molar ratio. Wherever we have unequal molar ratio, it is no more a double salt. So then this is forming a complex salt and does not give the test for copper ion, because it is forming a complex salt and the complex salt will have the formula of, this is quite common to you. You also have done the same thing as the test. So in aqueous solution, when copper sulfate and ammonia are taken in 1:4, it forms an azure blue solution, that is tetraamine copper 2 ion. In fact, this azure blue solution formation we have tested when aqueous solution of copper ion is treated with excess of ammonia. We first get the bluish white precipitate, that is due to formation of copper sulfate, followed by excess ammonia. That's why it is not in 1:1 ratio. Excess ammonia makes the solution soluble, makes the precipitate soluble, and that is due to one more point: all ionic coordination compounds or complexes are soluble in water. So this forms the ionic complex, and that makes the solution precipitate soluble. This color is azure blue. All that points why the solutions are colored, why the complexes, some of the complexes, means most of the complexes or ionic complexes are soluble in water. All these we will see in details later on. Okay, thank you dear. In case you find any difficulty in today's explanation, please feel free to clear your doubt, and I'll send the PDF also as the notes for this too. So you don't have to pause the video and write. I'll send the PDF in the official WhatsApp group only, and kindly go through this video explanation. Thank you dear.